In 39 through 42, we're asked to sketch the graph of each polynomial function considering the degree and behavior and zeros along with their multiplicities. So first we're going to calculate that leading term. The leading term here is x times x times x, which is x cubed. That makes it a third degree polynomial. And since the leading term has a 1 coefficient, which is a positive number, the right-hand behavior will be up. Since it's an odd degree, degree 3, the left-hand behavior will be opposite, which will be down. Okay, now let's next consider the multiplicities of each of the zeros. Our first factor is x. That's equal to 0 when x is 0. Since that factor is raised to the first power, the multiplicity is 1. The next factor is x plus 2. That's equal to 0 when x is negative 2, and that also has multiplicity 1. The next factor is x minus 5. That's equal to 0 when x is 5, and that also has multiplicity 1. So each of these zeros can be graphed as x-intercepts. And then our right-hand behavior is up, and since they're all multiplicity 1, the graph just passes through going up and down through each zero. In number 40, our leading term is negative 1 times x times x times x cubed. So that will be negative 1x to the 5th power. That's going to be a 5th degree polynomial. And since our leading term has a negative coefficient, negative 1, the right-hand behavior will be down. And since it's an odd degree polynomial, the left-hand behavior will be opposite, which will be up. So let's look at our factors. The first factor, x, is equal to 0 when x is 0, has multiplicity 1. The second factor, x plus 2, is equal to 0 when x is negative 2. That also has multiplicity 1. The third factor, x minus 3, is equal to 0 when x is 3, but this one has multiplicity 3 because it's raised to the third power. So now we're going to graph each of those intercepts, negative 2, 0, and 3. And our right-hand behavior is down, but as we approach the 0 at x equals 3, we know that it's going to flatten, but we need to have the right end heading downward, and then the left end is going to be heading upward, but it's going to come back down to that other 0, and since the other zeros are multiplicity 1, the graph's just going to basically pass straight through them. Make sure that you are exaggerating that flattening. So I'm going to do a better job here of exaggerating that flattening at x equals 3. In 41, our leading term is x times x squared times x. So that will be 1x to the 4th power. That's a 4th degree polynomial if it has a leading term of with degree 4. And since the leading coefficient is positive, positive 1, the right-hand behavior is up. Since the degree of the polynomial is even, 4, the left-hand behavior is the same direction or up also. Now let's take a look at each of our factors. X plus 2 is equal to 0 when x is negative 2. It has multiplicity 1 since it's raised to the first power. X minus 1 is equal to 0 when x is 1. This has multiplicity 2 since it's raised to the second power. X minus 5 is equal to 0 when x is 5. This has multiplicity 1 since it's raised to the first power. So let's graph each of our zeros at x equals negative 2, x equals 1, and x equals 5. Our right-hand behavior is up, and as we pass through x equals 5, that's a multiplicity 1, 0, so it's basically going to just pass straight through. At x equals 1, the graph will bounce off of the x-axis because it's multiplicity 2. And then at x equals negative 2, the graph's just basically going to pass straight through. In 42, our leading term is coefficient negative 1 times x cubed times x squared times x. So that is negative 1 times x raised to the 6th power. That's a 6th degree polynomial. And since it's a 6th degree polynomial with a negative coefficient, leading coefficient, our right-hand behavior is down. 6th degree polynomial is an even degree, so that means left-hand behavior is in the same direction, also down. Now let's take a look at each of our factors. So the first factor, variable factor here, is x plus 2. That's equal to 0 when x is negative 2, and has multiplicity 3 since it's raised to the third power. Second factor x minus 1 is equal to 0 when x is 1, and that's multiplicity 2 since it's raised to the second power. X plus 4 is equal to 0 when x is negative 4. That's multiplicity 1 since it's raised to the first power. All right, let's graph our zeros, negative 2 and 1 and also negative 4. And our right end behavior is down. And as we pass through x equals 1, the graph is going to bounce off of the x-axis. And so now we're heading back up to the next 0 at x equals negative 2. At x equals negative 2, the graph is going to pass through, but it's going to flatten out. And then it's going to pass through x equals negative 4 and basically pass straight through. We want to make sure we're exaggerating that flattening right there at the multiplicity 3, 0. In 43 through 46, we're writing the equation for a polynomial function in factored form. We're going to consider the zeros and their multiplicities, and then use the additional point to find the value of the leading coefficient. So we're going to start with those zeros. The zeros are x equals negative 2, and this one's a multiplicity 2, since it bounces off of the x-axis. And then we also have x equals 1 over here. That one's a multiplicity 1, since it basically just passes straight through. So our equation will look like this: y equals a times x plus 2 raised to the second power times x minus 1. So let's use our extra point to find the value of the lead coefficient. Extra point is 0, negative 3, which means that y is negative 3 whenever x is equal to 0. So replacing those values, we get an equation: negative 3 is equal to a times 0 plus 2 squared times 0 minus 1. Or negative 3 is equal to a times 4 times negative 1. So negative 3 is equal to negative 4 times a, dividing a is equal to positive 3/4. So that means that the equation of the polynomial is y equals 3/4 times x plus 2 squared times x minus 1. In 44, there are two zeros or x-intercepts. We have one at x equals 0. Notice the graph flattening as it passes through, so this is going to be a multiplicity 3, 0. And we also have a 0 over here at x equals negative 3. The graph just basically passes straight through, so that's multiplicity 1. That means that our equation will look like this: y equals a times x plus 3, no exponent on that one, or an understood exponent of 1, and then our other factor will be x minus 0, if you like, raised to the third power. Typically that's going to be written this way: ax cubed times x plus 3. Typically we write the monomial factor first. Alright, let's use our extra point to find the value of a. Extra point has coordinates negative 2, 3, so that means that y is 3 whenever x is negative 2. So that we're going to get an equation: 3 is equal to a times negative 2 cubed times negative 2 plus 3, or 3 is equal to a times negative 8 times 1. So 3 is equal to negative 8a, which means that a is negative 3/8, and the equation of the polynomial is y is equal to negative 3/8 times x cubed times x plus 3. In number 45, there are three zeros or three x-intercepts. We have one at x equals 3. That's going to be a multiplicity 1 since the graph is passing straight through. We have one at x equals 0. That's going to be multiplicity 1 since the graph is passing straight through. And we also have one here at x equals negative 4. That's also going to be multiplicity 1 since the graph just passes straight through. Alright, that means that our equation is going to look like the following: y equals a times, and I'm going to write that monomial factor of x, which is really x minus 0 first, and then we have a factor of x plus 4 for the 0 of negative 4, and a factor of x minus 3 for the 0 of x equals positive 3. From here, let's use our extra point to find the value of a. Extra point has coordinates of negative 2, negative 4, which means that y is negative 4 whenever x is negative 2. And So I'm going to replace all my x's with negative 2, which gives us an equation negative 4 is equal to a times negative 2 times negative 2 plus 4 times negative 2 minus 3. So negative 4 is equal to a times negative 2 times positive 2 times negative 5, or negative 4 is equal to positive 20 times a. That gives us an a value of negative 1/5. This means that y is equal to negative 1/5 times x plus 4 times x minus 3, and that is the equation of the polynomial function. In number 46, there are only two zeros. There's one at x equals 2. That one bounces off the x-axis there, so that's going to be multiplicity 2. And at x equals negative 2, our graph is passing through, however, it is flattening. So due to that, we're going to call this one a multiplicity 3, 0. So our equation will look like the following. Y is equal to a times x plus 2, that's for our negative 2, 0, which is raised to the third power, times x minus 2, which is for our x equals positive 2, and that one's raised to the second power. Let's use our extra point here to find the value of a. And our extra point has coordinates of 0, 3, which means that y is equal to 3 whenever x is equal to 0, giving us an equation 3 is equal to a times 0 plus 2 cubed times 0 minus 2 squared. So 3 is equal to a times 8, and remember negative 2 squared is positive 4, so 3 is equal to 32 times a, and a is 3/32, which gives us an equation y is equal to 3/32 times x plus 2 cubed times x minus 2 squared.